Next topic will be state estimation in nonlinear dynamic systems, since a lot of the systems we are handling in engineering will be nonlinear and cannot be easily modeled as linear. We have to figure out some techniques that allow us to do estimation in this situation. So, what we are going to do is discuss briefly the optimal discrete time state estimator for nonlinear dynamic systems, and we'll discuss the difficulty in implementing it in practice due to memory requirements and computational requirements. And we'll compare an optimal nonlinear estimator to the best linear estimator for a simple nonlinear problem, just to get a feel for the benefit from using nonlinear techniques. Then we'll go on and discuss a suboptimal filter, which is a linearized version of the Kalman filter, called the extended Kalman filter. Effectively, we will linearize the nonlinear system and end up with a linear filter for it, clearly an approximation. And we'll discuss some of the problems that can be encountered when this is implemented, and some compensation methods are also covered towards the end of this chapter. Nonlinear stochastic systems can be modeled by a difference equation. Again, in discrete time, x at time k plus 1 is some vector valued function time k, so it is time varying system, of the state at xk, of the known input uk, and the process noise vk that covers the interval from k to k plus 1. In general, we have this nonlinear manner in which both x, u, and v appear on the right hand side. However, in most cases, even for nonlinear systems, v will enter linearly, so we'll have this boldface f replaced by a regular f that simplifies to some extent the equations. And zk will be another vector valued function h of k and x and w of k, that's the measurement noise. Again, for the more common case where the additive measurement noise is a suitable model, we'll take it out of the nonlinear function and we'll use a regular h and plus a w. So, in order to have a nonlinear problem, at least one of the above functions has to be nonlinear. The noise sequences will be assumed, as in the linear case, to be white with known PDF and mutually independent, not necessarily Gaussian, obviously. The initial state will be assumed also to have a known PDF and be independent of the noise sequences. So the same three uncertainties and the mutual independence between them and the whiteness are critical, and the reason for this is the Markov property that is required, and this will come out from our derivations. The main result will be that the optimal nonlinear state estimator consists of the computation of the conditional probability density function of the state xk, given all the information available at time k. So whatever is a state in a deterministic case, its probability density function will summarize the past, and that's all we have to do, as we'll see in the presence of white noises. Obviously, to this we have to add the fact that there's a prior information about the initial state that will be needed, and when we use this PDF of the state, the intervening inputs and the measurements through time k will be appearing in the conditioning. in a general nonlinear problem, there is an information set available at time k. And this information set I super k consists of z super k and u super k minus 1. Z super k is the cumulative set of observations through time k, which includes the initial information z0. And u super k minus 1 is the set of known inputs prior to time k. The problem with this I super k is that it is growing with k. It would be desirable to have a non-growing information state. It might be large, but it should not be growing with time. And obviously it should summarize the past in a manner appropriate for the problem. Namely, we can answer all probabilistic questions about the future evolution of the state. For a stochastic system, one which evolves in the presence of uncertainties, an information state will be a function of the available information set, which completely summarizes the past of the system in the probabilistic sense. It is a complete substitute for the past data when we ask the question, what is the probability density function of any present and future quantity related to the system? Namely, with the information state, we can evaluate the PDF of any future state or future output from the system. It turns out that the conditional PDF, denoted very succinctly by P sub k, which is a very shorthand notation of the PDF of x at time k given I super k, does satisfy this requirement if the two noise sequences, process and measurement, are wide and mutually independent. Of course, there is also the initial state, which is another random variable, which should be also independent of those noises. That is the third condition, which was mentioned earlier in the linear case. Now, the optimal estimator consists of a recursive functional relationship between the information states pk plus 1 and pk. Pk plus 1 is the PDF of x at k plus 1 given I k plus 1, and pk is the previous version of it. So it turns out that this pk plus 1 is given by the PDF of the measurement at k plus 1, the new information, given xk plus 1. This is the likelihood function at time k plus 1 of the new state xk plus 1, times something which brings the previous information to the current time. pk is the PDF of the state at time k given the information available at time k. Pxk plus 1 given xk and uk is the propagation of the state from time k to time k plus 1. So this really summarizes the dynamic evolution of the state, the dynamic equation. This summarizes the information available at time k, and this brings in the new information at time k plus 1. Now, mathematically, what we have here is an integration over the entire domain of xk. This is a normalization constant here. So we can see that there is a potential numerical problem that has to be overcome in this integration, as well as the ability to store and do manipulations on this probability density function. Okay, a number of additional remarks should be made about this optimal estimation equation. As indicated, it requires the storage of a PDF. Now, what is a PDF? In general, a PDF is equivalent to an infinite dimensional vector. So that's one of the problems. The second is the numerical integration. Now, in spite of these difficulties, the use of the information state has the following advantages. It can be approximated over a grid of points or by a piecewise analytical function, and it yields, if we have the PDF, relatively easily the minimum mean square error estimate of the current state, the conditional mean, and any other desired information that is pertaining to the current state. One of them obviously will be the conditional variance, the accuracy of our estimation scheme. So there are approximation techniques, and we'll discuss in more detail one of them. Now, for linear systems with Gaussian noises and Gaussian initial state, and obviously white noises, the functional recursion that we have mentioned before does become the Kalman filter. In this case, we have a finite dimensional sufficient statistic. The probability density function, if Gaussian, is fully specified by the conditional mean and conditional covariance. And this summarizes completely the past in a probabilistic sense. So the complicated equation does boil down to something very nice, finite dimensional, and we have seen the solution as a recursion for those two moments. Now, if the system is linear, but the noises and or the initial condition are not Gaussian, there is no simple sufficient statistic, no exact sufficient statistic that is simple, and the recursion that we have shown should be used to obtain the optimal minimum mean square error estimator. So what we've seen is there is an answer to the nonlinear estimation, which really is a consequence of Bayes' formula. And what we are going to do is show a simple example that compares the optimum and the linear minimum mean square error estimators for a linear problem with uniformly distributed random variables. So the problem is linear, but there is a solution to it which is better than the linear solution, because the random variables are not Gaussian. In this case, with the linear system, if you want to solve it optimally, you still, due to the fact that you have non-Gaussian random variables, you should still use a nonlinear estimator for the optimal solution. Obviously, if this is too expensive to come up with a minimum mean square error estimator, that's the best optimal, you can use a linear solution, which is suboptimal for the linear system because the noises are not Gaussian. Nevertheless, it might be close enough to optimal. First thing we'll do is we'll briefly go over the derivation of the optimal nonlinear estimator to understand these whiteness requirements. That's very important, and this is the place where they come out in a very clear manner. With Bayes' formula, if we want the conditional density of xk plus 1 at time where we have the information set ik plus 1, so this is the p sub k plus 1, which is the notation for p of x at k plus 1 given I superscript k plus 1. Now we can partition this ik plus 1 into ik, zk plus 1, and uk. This is the past information, this is the latest information. Once we do this, we will use Bayes' formula to switch between x and z. That's what we want. So, with this, we are going to switch and write Bayes' formula that p of xk plus 1 given ik and zk plus 1 and uk is, first a normalization constant that's not relevant right now, is p zk plus 1 given xk plus 1 ik and uk. So just switch these two times the PDF of xk plus 1 given the right hand side except zk plus 1. So this is given the past information, and obviously we put in the known input because it is necessary to specify, but what is random is this ik in general. That's our information as we gather it. So now what do we need for the measurement noise? We need a measurement noise to be white in the following case: wk plus 1, condition on xk plus 1 has to be independent of the past w's. So that's k plus 1. Here the j index of w goes up to k. Actually, it turns out state-dependent measurement noise is okay, but it should be still white. And of all the process noises, again up to and including k. So that says the two noise sequences have to be independent. In that case, the first term, pzk plus 1 given xk plus 1 ik uk. It's here. Pzk plus 1 given xk plus 1 ik and uk really depends only on xk plus 1. Because if I know xk plus 1, all I need is w. So this, the only uncertainty that takes me from x at k plus 1 to zk plus 1 is the w. The past knowledge of the past data, ik, and of the input is of no consequence. This is the likelihood function of xk plus 1 at time k plus 1 given only the latest information. So what we have now is a clear reasoning why we need white measurement noise. Next one will be the prediction. The PDF of xk plus 1 given the past for an arbitrary value of the known input or control at time k, that's uk. We have a state prediction PDF. It's really a function as opposed to a point prediction, not just the predicted value as in the linear case. We had the value, predicted state, and the covariance. That in the linear Gaussian case is everything that's needed. Now we have a PDF. So here is the PDF of xk plus 1 given the past information, ik. This can be written as you add a conditioning xk and you remove by multiplying it with the PDF of that extra conditioning given the past, ik, uk, and integrate it out. So this is exactly like the total probability theorem, which we now use in order to bring in the role of the process noise. What really matters in the evolution of the state, its dynamic equation. Now, this is really a consequence of the total probability theorem. It is also known as the Chapman-Kolmogorov equation. Now, if we assume that the process noise sequence is white and independent of the measurement noises, and again, Vk, conditioned on xk is independent of all the past v's and w's up to the latest time, that's whiteness of Vk. And this is really the same thing as requiring the state vector x to be a Markov process. Then we'll be able to simplify this equation as follows. Pxk plus 1 given xk, ik, uk really depends on only xk. The ik is irrelevant because ik contains past measurement noises and earlier process noises. Therefore, in view of the whiteness and the mutual independence between the two sequences, is inconsequential, and the only thing that has an effect here is the process noise Vk, which is the only additional thing that makes the realization of x at k plus 1 random, given that, assume here in the conditioning, we know xk and uk. So this is the state transition probability density function. This summarizes really all the statistical or probabilistic properties of the state's dynamic equation. Even UK is irrelevant in the equation Pxk Ik UK, which is the second term here, which we added in order to use the total probability theorem. So from here UK can be eliminated. And this is exactly Pk. This is our information state at time k, and now we have the justification for it, because the prediction PDF for the state, that's Pxk plus 1, given the past and one more input, turns out to be a function only of Pk. That's the first of the two steps. So what we have, phi, is an operator which maps the function Pk into another function that is the state prediction probability density function. So this Pk is mapped into this, from which we have one more step. When we use this expression in the original base formula, we find that Pk plus 1 is another operator, psi, function of k plus 1, Pk, the new measurement, and the intervening input. So this is a full functional recursion for the information state, rewritten explicitly in a manner that is clear that Pk is now an information state. So this proves that Pk does obey a recursion when we propagate one step at a time, and we'll show that for any future state it is the same Pk that summarizes the past. So the final argument that will show that Pk is indeed an information state is that the PDF of any future state at j greater than k depends only on Pk and the intervening known inputs. These known inputs from time k to time j minus 1 are denoted as cap u sub k super j minus 1. That's really the set u sub I going from k to j minus 1. So this u of I, these u of i's are all the intervening inputs in the interval starting at k and ending at j minus 1. Again, with the total probability theorem, we can write for some j greater than k, for any j greater than k, as a matter of fact, p of x at this future time j, given the information at the present time and all the intervening controls from now up to j minus 1, that's all we need, is integral pxj, future time j, given the present xk. So we add this conditioning here, ik and uk to j minus 1, and multiply pxk ik. So we add the conditioning and remove it by multiplying it with its PDF and integrating over it. So what we have here, this expression is really my Pk. So what I have is this future states PDF is some functional of Pk and the intervening inputs. This is going to reflect the dynamics from time k to time j. That's the state prediction. So all we need is Pk to answer any probabilistic, or to answer in a probabilistic manner, any question about a future state xj. The whiteness of the process noise sequence and its independence from the measurement noises have been used again. Namely, here we drop Ik. This has past process noises and measurement noises, irrelevant. Why? Because only white noises here matter and they are independent. So there's nothing that this adds. I super k will add nothing to this PDF. Therefore, I super k is summarized by p sub k. So, the whiteness and mutual independence of the two noise sequences is a sufficient condition for pk to be an information state. Whiteness is really the crucial assumption. These conditions are equivalent to the requirement that xk be an incompletely observed Markov process. Through the dynamic equation driven by white noise, it is a Markov process. In addition, it is observed partially or in the presence of noise via zk. So what we have is incomplete, imperfect observation on a state which evolves driven by white noise. Now, if the process noise is not a white sequence, it is obvious that pk does not summarize the past data, because in this case the vector x is not a state anymore. It has to be augmented. Once it is augmented, then we have a new larger dimension vector driven by white noise, and we have all the conditions satisfied. So this points out the reason why the formulation of stochastic estimation and also control problems is done with mutually independent white noise sequences. And here's the example, and this is a fairly simple example where we have a linear problem with non-Gaussian noises, for which if you want the optimal solution, you cannot use linear estimation. So we'll provide a non-linear solution through base formula in a manner similar to what we just derived for the dynamic situation. This is a static problem, so it's easier to evaluate. So we have uniform PDFs, and we want a non-linear solution, and in addition to it, compare it in terms of quality to the linear solution. And there will be a certain quirk when we want to make the comparison. It has to be done carefully. So we have an unknown parameter x with a uniform prior in the interval x1, x2. So px is uniform argument x, interval is x1, x2, the difference of two step functions, one starting at x1, the other one starting at x2, divided by the distance between them. And we make a measurement. Measurement is linear, but again the measurement noise is non-Gaussian. So the prior is non-Gaussian, the measurement noise is non-Gaussian. The two noise uncertainties, the W measurement noise is independent of x, which means the initial uncertainty in x and the observation uncertainty are independent. That's one of the conditions we need in a dynamic situation as well. And this W is uniform in the -a to +a interval. So P of W is uniform argument W starting at -a, ending at +a, which can be written with unit step functions, one of W plus a that starts at -a, where the argument of the unit step function equals to 0, and at W equal to a, at the point where W minus a equal to 0, it ends because past this point it is 1 minus 1. So this is the location. One step function at -a, the other step function starts at +a, and divide by the length of the interval to make sure it integrates to 1. So this is the formulation of the problem. How do we get the optimal estimator? The conditional mean. We want it, we need a conditional PDF. P of x given z is P of z given x, px over pz. Second, the denominator is just the normalization factor. This is the likelihood function, P of z given x, the likelihood function of x given z. P of z given x, if we know x, where can z be? Uniform from x minus a to x plus a. That's because the noise was uniform between minus a and plus a. So we have again two-step functions. Argument is z. It starts at x minus a, so it's 1 of z minus x minus a, and it ends at z equal x plus a, so the second step function is 1 of z minus x plus a. Using the prior and the likelihood function, prior here, the likelihood function here. We put this all in the base formula, and we have the difference. This is the likelihood function. Equation 5 is here. The prior is here. And there are some constants from each of these two densities, and the P of z, which it's really just the final normalization factor. So this is, or can be written as a uniform density in X, where it starts at the largest of the two values, z minus a and x, between z minus a and x1, and it ends at the smaller of the following two values, z plus a and x2. Clearly it cannot start before x1 because that's the prior. It cannot start before z minus a in the space x, because that's the worst case of noise that you can get, a minus a reducing the value of the observation. So what you get here is the largest of this up to the smallest of these two quantities, and these are the notations we use: max between a and b and min between a and b. Now what we have is that the conditional PDF we just derived is uniform in the interval, which is the intersection of the x1, x2 interval based on the prior, and the z minus a to z plus a interval. This is the feasibility region of x given z. The minimum mean square error estimator of x given z, and this is the exact conditional mean, is the midpoint of this uniform, where the one point is the largest of z minus a and x1, the other point is the smallest between z plus a and x2, and take the sum, divide by 2. So that's the midpoint of our interval. However, these two operations, smallest and largest, are non-linear operations. Therefore, we ended up with a non-linear function of the measurement z. So what we have now is a fairly easy to write, in this case, solution to a non-linear estimation problem. Next question is, how good is it? And the answer to this will be given by the conditional variance of this estimator, which will be for a given z. If you have the z, the pxx given z, that's the notation same as we used in the linear estimation situation, which is the variance of x given z, is just the length of this uniform distribution, the length of the interval over which it is non-zero squared divided by 2. This is the expression of the variance of a uniform density. Now, there is an interesting thing we see immediately. The accuracy of the optimal estimate measured in terms of its variance is measurement dependent. For different values of z, you get different values of the variance. This is a major departure from what we have seen in the case of linear estimators, where the variances were all data independent, observation independent. So let's put this aside. We have solved the optimal problem. Now we want to solve the same problem with a linear solution. The linear minimum mean square error estimator of x in terms of z is given by the fundamental equation of linear estimation. X L MMSE hat here is x bar, the prior mean, plus pxz, pzz inverse z minus z bar. X bar is the mean of x prior. It's x1 plus x2 over 2, the midpoint of its uniform prior distribution. The z bar expected value is just the same as x bar because w was modeled as uniform between minus a and plus a, so it's zero mean, does not contribute to the mean. The covariance between the variable of interest x and the variable we're observing z is ex minus x bar, z minus z bar, and because x minus x bar, that's deviation of x from its mean, and w are uncorrelated and zero mean, the cross term falls out and I end up with the variance of x. So pxz is really the same as pxx, the prior variance of x, which is the length of its, that's called the support of the uniform prior distribution, the points where it is non-zero, squared over 12. Second is pzz. This is the expected value of z minus z bar, but z is x plus w. Z bar is x bar, so we substitute, reorder these terms here, and see that there is an x minus x bar squared after expectation, that's the pxx. There's a w square with expectation is pww. There's no cross term, again, for the same reason as here there was no cross term, they are orthogonal. W is independent of x and zero mean, so they are ending up with two terms. One of them will be the same as before, x1 minus x2 squared over 12. The other one is the variance of a uniform random variable that the support of its PDF is 2a, because it's from minus a to plus a, so it's 2a, the whole thing squared, divided by 12. So here is the variance of z. And the mean square error corresponding to our best linear estimator can be written as pxx minus, turns out the pxz, because these are scalars, that's a squared over pzz. Can manipulate this and you end up with back to the parallel resistors formula. Pxx, pww over pxx plus pww. Pxx is the prior variance, pww is the variance of the measurement noise. Now, next thing we would like is to compare the optimal. We solve the two problems and we would like to compare them. How do we do this? The comparison between the errors obtained from the optimal and the best linear methods cannot be made between the conditional variance that we have obtained for, this is a mean square error from the best linear estimator, and this is the conditional variance pxxz that we have had at the end of the solution of the problem with base formula. Because in the nonlinear solution, the conditional variance is a function of the observations. So what value do you give to the observation? It's not clear. So what we have to do now is compare the variance from the best linear technique, which is independent of z, with the average over the conditional variance given z over all the possible measurements z. This is the correct way of making the comparison. One is measurement independent, one is measurement dependent. That's almost like apples and oranges. So what we do with the measurement dependent one, we average it over all the possible values of z. So now we take the pxx given z, take its expected value, and we say this is the average over the conditional variance. So this includes the fact that the information is available, but we remove it and take an average value over all the possible information values, the values of z, the observation that we could have gotten. So it's integral cap p sub xx given z, that's a variance. This little p is a PDF times pz dz. So really pz is that the density pz, which we did not need before because it was independent of x, is the convolution of the two uniforms of the prior between x1 and x2 for x, and the density of the measurement noise, which is between minus a and plus a. So those are the two densities, can be easily convolved, give you a triangular density. What we have next is the results of this comparison once they have been brought in the same context. And we'll have some numbers. The interval over which x is uniformly distributed is taken as 1. So the prior variance is 0.0833, 1 over 12. Then we vary the measurement from very accurate, namely a much smaller than 1, to very inaccurate, practically non-informative for a much larger than 1. So keep one thing fixed and vary the other one. And for various values of a 0.05, that's a very accurate measurement, the optimal gives us 7.6 something, 10 to the minus 4. The linear estimator gives 8 and a quarter, 10 to the minus 4. So you can see there is some benefit. At one extreme, you see approximately 8% or so decrease in the variance from the linear to the optimum. At the other extreme, A is 5, it's 100 times worse in standard deviation, actually 10 to the 4 in variance, because this is linear in A, the standard deviation. The optimal is 8.12, 10 to the minus 2. The linear is 8.25, 10 to the minus 2. The difference between them right now is very small, is approximately 1 over 80 by now. So we end up with a very small difference for a very accurate measurement versus a very inaccurate measurement. In between, we'll see. The benefit of nonlinear estimation is, in this case, kind of disappointingly modest. 1% for the inaccurate measurement considered, around 1 over 80, that's close to 1%, to 6% for the accurate measurement. Again, these are for the specific numbers. As you change the numbers, you'll get different. But we can see it is fairly small. What is interesting is the maximum. In the mid-range, you benefit about 15% in variance. How much is 15% in variance? Is like the square root of 1.15 being 1.07 approximately. You are down to a 7% improvement in standard deviation. So clearly this is a toy or academic example. Each problem requires its own evaluation. But for a linear problem, when you have non-Gaussian random variables, you can see that there is no great benefit from using nonlinear estimation. The other nonlinear problems where nonlinear estimation probably is more beneficial. In particular, there are some dynamic problems.